Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Early 20th century mathematicians like Emmy Noether introduced homology to lift numerical invariants such as Betti numbers up to algebraic invariants like the homology groups. And so the study of homology is often to deal with numerical invariants in a more sophisticated way, a way where you can track more information. And this is also true about cohomology in algebraic geometry as well. So it's used often to find out a lot about numerical invariance. And what I want to do in this video is to show you how cohomology theory can be used to understand the numerical theory of intersections of curves on surfaces. So to motivate what's going on, I want to have a look at just the local theory first of intersections. And I just want to choose a little simple example. There's going to be this one inside the affine plane A2 with coordinates x and y. And we're going to pick two curves in here. This blue one here is just going to be given by this cubic equation, x cubed minus x squared equals minus y equals 0. So this polynomial in x and y I'll denote by f of xy, so it's basically the graph y equals x cubed minus x squared. So you've got a double 0 here, and at x equals 0, and you've got another 0 at x equals 1. And the other curve that I have is this purple C curve, which is given by the x-axis y equals 0. So it's this one here. Okay. So what I want to do is I want to talk about what's the intersection of these two curves and what's the intersection number. So how many times do they intersect? Well, if you just count the points, of course, there are 2 points here. But to make the theory work out nicely, what we want to do actually is when we look at this point here, P, we want to say that it intersects doubly. Okay, it's a double point. And that's because when you think about it, the intersection multiplicity here, it's going to be order 2. This is like a double root. Okay, so this is multiplicity 2. And this point here, Q, however, has multiplicity 1. Okay, so the way we wanted to define it, actually, C dot D in this little example here, is what we can do is we can take the equation for this D here, as given by this cubic polynomial, okay, and we're just interested in what that is on C. So we restrict this cubic polynomial to C. So inside C, you're working inside the coordinate ring of C, which is just isomorphic to k of x, and that you get by just setting y equals 0. So when you set y equals 0 here, you just get x cubed minus x. Okay, so you're going to look at this polynomial, and you want to see where is it 0 on here, so you restrict that polynomial to here and look at its zeros. Count the number of zeros. Of course, you just want the number of zeros this, but you want to count multiplicity, so there are going to be 3 of them. Okay, so that's an example of what I mean by intersection numbers. Okay, so one of the things that you have to include is there's a certain multiplicity, and it's quite easy to see what's going on here. Okay, and this is something that you see often enough when you look at solving polynomial equations. Okay, so this example suggests what we should do in general, and now I want to move away from the affine setting to the projective setting, where intersection theory really comes to the fore because it satisfies a lot of interesting properties. Okay, so let's suppose now we move to X is a projective variety over my algebraically closed field K, and what we'll need is we're going to need a curve here, C, and we want to have some Cartier divisor D. Okay, so this will be codimension 1, and this is dimension 1. And so in general, if you have something codimension 1 and something dimension 1, if they intersect, if the curve is not on that codimension 1 variety, then they will intersect in a finite number of points. And then you can talk about the intersection number, which is not just the number of points, but the number of points included with multiplicity, as we've seen in this little example here. Okay, so let's just see what the definition should be. So in this case, the definition is very simple to produce. Okay, the intersection number C dot D of this curve with this Cartier divisor is just going to be, we're going to use a similar prescription to what we've done here. Okay, we take now to this Cartier divisor, remember you can construct this line bundle, this invertible sheaf OXD. And this is a line bundle on all of x, so you can restrict it now to this curve. So now you have a line bundle, this invertible sheaf on C. And since this curve C is a projective curve, you can talk about the degree of this. Okay. Often this restriction is denoted O subscript C D, and we'll do that in the future. Okay, and this will do exactly what you want. Okay, this will recover this situation precisely. Okay, so that's definition is suggested by examples such as these. So let's go back to this example. This is not projective, so we'll need to make it projective. So we'll do that by embedding this affine plane into XYZ projective plane. C is still given by y equals 0. But D, I guess we'll have to homogenize this equation by introducing Z to make it cubic. So it's given by x cubed minus x squared z minus yz squared equals 0. And then what you want to do, you want to have to look at, well, what is this invertible sheaf here? So you've got to take this, this divisor, Cartier divisor, okay? And the way you'll do that is you look at local equations for this. So it's essentially by getting this. And what you want to do is you want to restrict this local equation, this function, you pull it back up to the C, and you look at the zeros there. So when you look at the zeros here, you'll find there are 2 of them at P. So what this will end up being is it's just 2P plus Q. Okay? And of course, this has degree 3, so that's how it recovers your answer. And you can see here clearly how this is just a simple realization of your the process of computing intersection numbers given here. What's really nice about this definition here is it immediately gives us 2 very interesting properties of this intersection number. So the first one is that, well, here, you only care about this invertible sheaf OXD, okay? If you replace D with something that's linearly equivalent, of course this the isomorphism class of this sheaf does not change. So that means that if you change D to something linearly equivalent, okay, this intersection number stays the same. And the way you should kind of think about this is that if you make a linear deformation of this Cartier divisor D, you make some sort of linear deformation of that, you don't change the number of points of intersection, okay? Some of the points of intersection may come together. So for example, if you shift this up, these 2 will separate, and when you bring it down, sometimes they may collide. But if you look at the total number and include the multiplicities, then you will always get a constant. It doesn't matter how you make these linear deformations. The other thing that's clear is that, well, the degree is a group homomorphism, okay? So it's additive in this D. So you have this linearity in this D variable here, okay? So that's also a very nice property. Okay, so let's move to the general theory for smooth curves, okay? So we're going to look at intersections on smooth curves. How does that work? So X here will now always be a smooth projective surface. And we're going to consider, again, an irreducible curve, C, okay? And since we're on a smooth surface, all Weil divisors are Cartier, so this is automatically a Cartier divisor, okay? We'll also have a divisor D on X, which is just some integer linear combination of curves in this case. So in this case, the asymmetry you see is less because both for the D and the C, you have things which are one-dimensional, okay? Because codimension 1 equals dimension 1 when the dimension you're working in is 2. Okay, so what the proposition now says is that if you look at this C dot D, okay, I'm going to write this purely in terms of cohomology, okay? This is some sort of a numerical invariant, you can think of it that way. And I want to do it just in terms of cohomology. And in fact, I'm just going to use the Euler characteristic. So C dot D is just chi of the structure sheaf OX minus chi of O minus C minus chi of O minus D plus chi of O minus C minus D. Okay, so you just look at these 1, 2, 3, 4 line bundles. You look at the Euler characteristics of them, and you make this sum with the negatives here and the positives on these outside ones like that. And the proof of this is fairly simple. And I'll do it in the case where C is not contained inside D. Otherwise, you can't. We can use this description, but you need to think about precisely more what that means. Okay, so let's see what happens. So the first thing we're going to do is we're going to look at, so what is the structure sheaf on C? Okay, so basically it's just the structure sheaf on X modulo the ideal of functions or ideal sheaf of functions vanishing on C. So that's OX minus C. So you have this short exact sequence. You can take this short exact sequence, and of course you can tensor by any invertible sheaf that's an exact functor. Okay, so if we tensor it by O minus D, you get OC minus D. You get OX becomes O minus D, and the OX minus C becomes O minus C minus D. Okay, so you have this exact sequence as well. Okay, so what's C dot D? Now we're ready to compute this intersection number C dot D. Okay, C dot D is going to be just the degree of OC plus D. But we want to work with OC minus D, okay? But remember, this degree of this is going to be, oh, no, it's the degree just of OCD. It's not the degree of chi of that, it's just the degree of OCD. And of course, remember, this is additive in that variable. So if you want the degree of OCD, that's just the negative of the degree of OC minus D. So let's have a look at OC minus D. Remember, the other thing, and this is kind of the reason why the Euler characteristic is so nice, is that it's additive on short exact sequences. So the Euler characteristic of this, okay, is the difference of the Euler characteristics of these, for example. Okay. So here you want to look at the degree of this, and what does Riemann-Roch do? Riemann-Roch changes this degree in terms of Euler characteristics. Okay. So the Euler characteristic of this, okay, term here, which normally you'd have on the other side, is the sum of the Euler characteristic of the structure sheaf on the curve plus the degree of that line bundle, or that invertible sheaf, which is this one here. That's why there's a negative there. So this first step shows by Riemann-Roch that C dot D is just the difference between these Euler characteristics of OC and OC minus D. Now we can work out these Euler characteristics using these short exact sequence. Chi of OC, remember the Euler characteristic is additive on short exact sequence, so it's just chi of OX minus chi of O minus C, chi of OX minus chi of O minus C, and then you have to subtract chi of OC minus D, and that's of course just the difference of the Euler characteristics of these two. That's chi of O minus D here, and chi of O minus C minus D over here. And when you expand it, okay, what are these four terms? You get the chi of O here, the minus chi of O minus C here, the negative chi of O minus D here, and the minus minus gives you a plus of chi of O minus C minus D here. Okay, so that gives you a lovely formula for what C dot D is, which is given in terms of cohomology. Okay, and the big theorem, which I won't prove, is that, well, what's kind of nice about this is that to define this, okay, you didn't need C to be an irreducible curve on C. You could replace it with any divisor that you like, right? Put any divisor, the formula on the right hand side still makes sense. So you can use formula star to define a map from a pair of divisors, C and D, okay, to an integer. And in fact, what this will do is, if you use this formula star, you get a symmetric bilinear pairing from pic x cross pic x to z. Okay, so how does that work? Well, the first thing to note is that, yeah, I guess it's quite easy to get a, so to get linearity, okay, so if C is something which is an irreducible curve, you've seen that it's additive in that variable D. And what's kind of nice here is that not only is it additive in the variable D, but it's also additive in the variable C, this formula, okay? And that you can believe because it's symmetric in C and D, okay? That also gives you the symmetry, right? So that tells you why that's true, okay? And so what it also means is that this definition shows also that it only depends on the linear equivalence class of C as well. So that means that you can move the C around in its linear equivalence class and it won't change. Okay, so this is something that's a very, very useful fact, to know that you have this tool called this intersection number, which pairs up linear equivalence classes of divisors, or known as pic x, or the known as pic x, to give you an integer. Okay, so hopefully you've seen my video on Bezout's theorem. One of the things that we can do now is that with this theory we can easily recover Bezout's theorem in a very, very nice and succinct way. So let's just remind ourselves what Bezout's theorem is about. It's about plane curves. Okay, so you have plane curves here, C and D, inside the projective plane P2. And the key numerical ingredient that's given for these two is just their degrees, C and D, say, for example. And in this case, you might want to work out what is the intersection number, C dot D. Then the intersection number is just the product of those two degrees, C times D. So what this tells you that in particular is that the number of intersection points of these two curves, so if these are actually two, so these are curves of degrees C and D, the number of intersection points is going to be, if they are actually have no common components, okay, is, so if they have common components, it will be infinite, but if they don't have common components, it's going to be finite, and the number of intersection points is CD if you count multiplicity. And if you don't count multiplicity, it'll be at most CD. So this does actually give actual information about the set theoretic intersection, okay? So that's a wonderful theorem, okay? It's about as nice a formula as you can get. And the nice theory, how it's set up, should indicate that you know, it should come out of some nice general procedure, and that's how it works here, okay? So what we're going to do is we're just going to use this formula and see that the intersection number is indeed C times D. So let's see how it's easy to compute in this case. Okay, so we need some Euler characteristics of some invertible sheaves like O minus C. So what's O minus C? So since C has degree C, that means this is just isomorphic to O minus that number C, that degree C, and O minus big D is isomorphic to the sheaf O minus D here, like that. Okay, so remember what these are. So if you take any line inside P2, okay, you can think of this as O minus C times a line, and this is O minus D times a line. Okay, so that's the first thing, is that you have this these isomorphisms. And similarly, you can see that O minus C minus D is just O negative, the degree here will be C plus D. Okay. And the next thing is we need to be able to work out what are the Euler characteristics of these line bundles. So in general, what is chi of ON? And let me show you a very nice simple way to compute what that is, that uses a lot of the theory that we've already set up. Okay, so the first thing is that we have Serre vanishing. When n is very large, okay, as long as it's sufficiently large, okay, all the high cohomology will vanish. So the only thing that you're looking at when you look at this alternating sum is H0. So for n large enough, it's just little h0 of ON. And what is little h0 of ON? The global sections of ON. Well, to get that, what you do is you look at the homogeneous coordinate ring, k, x, y, z. You look at the degree n part of that, and you look at the dimension of that. Okay. So you look at the dimension of that, and so if n is greater than or equal to 0, so if n is negative, of course, this is just 0. But if n is non-negative, then it's quite easy to work out how many monomials there are of degree n. It's a simple exercise in combinatorics, and it's just n plus 2 choose 2, okay, or half n plus 1 times n plus 2. So this tells you that chi of ON equals half n plus 1 times n plus 2 when n is very large. And at the moment, with the argument as we've given it, because in this Serre vanishing, it's not effective, we don't know how large it is before it's true. But the other thing that we know is that this certainly is a polynomial in n. And the other thing is that this is a Hilbert polynomial, the Hilbert-Serre polynomial. And so this is also a polynomial. So these two polynomials have to agree on infinitely many values of n. So they must be the same for all n, in fact. So this is going to hold true even for negative values of n. Okay, even though when you look at what's happened, this equality here doesn't hold for negative values of n, just from the fact that we know that this has to be a polynomial. Since these two polynomials agree on sufficiently large values of n, they actually agree for all n. And now that means that with this, we can just plug into this formula star and compute what the answer is. So when we have O, that's O0, so n equals 0. So you have 1 times 2 is 2 divided by 2, that's 1. And then you have n equals minus c, so you have half 1 minus c, 2 minus c. N equals minus d, half 1 minus d, 2 minus d. And then n equals c plus d, or minus c minus d rather, so you get half 1 minus c minus d times 2 minus c minus d. And then you can just work out what this is. So let's just check some of the terms to see what you get. So what's the constant here? You have a 1 here. You get a negative half times 2, so there's a minus 1 here, so they cancel. you'll get a negative half times 2, so that's a minus 1 here, which cancels with this half times 1 times 2, so it cancels with that 1, so there's a 0 constant term there. And you can quite easily see that all the c squared and c terms cancel. For example, you'll have negative half c squared here, and then you'll get a plus half c squared over here. And then in terms of the c terms, you get minus 2c minus 3c plus that, of course, plus 3c on 2. Okay, and that cancels with this minus 3c on 2. And the c and d are symmetric, so they're going to be the same. And the only extra terms that you have floating around here are the cross terms with c and d. Okay, and so you get minus c times minus d twice inside here. Okay, so that gives you plus cd twice, and when you halve that, you get the cd. And that's what you want in Bezout's theorem. Okay, so this is a lovely way to recover Bezout's theorem in quite a different way to proving it using other methods. Okay, but uses the machinery of cohomology in a very, very interesting way. Okay, so this is a wonderful application. It also shows you how you can try to generalize this type of Bezout's theorem. In general, the general theory of Bezout's or the general version of Bezout's theorem is just to say, what is this map from pic x cross pic x to z? What is that intersection number map? Okay, here it's just essentially you have degree c dot degree d, it gets mapped to degree c times d, and that's because it's bilinear. Okay, so that's another way to do that. Okay, you can just set that up that way, but here I just did it straight from the definitions. Okay, so the other thing that I wanted to mention is that it's to give a sort of a different viewpoint of this little formula here. Okay, so another way to think about that is that, well, surely if you want to look at the intersection of c and d, you should just look at c intersect d. Okay, so let's have a look at c intersect d, and in fact you can talk about this in a scheme theoretic sense. Okay, so but let's suppose firstly that you have c and d, maybe they're actual curves, and irreducible curves, and the support of c is not contained in the support of d. Okay, in which case you can look at OC intersect d, and you should just look at that to be able to work out what is the intersection number. And the answer is yes. What you can do is you just can look at chi of this. So this should be a finite set of points. In fact, if they intersect transversely, okay, it will be just skyscraper sheaves. Okay, just direct sum of skyscraper sheaves. Okay, and chi of this will just correspond to h0 because of Grothendieck vanishing. Okay, this is supported in dimension 0, so you just only need to look at h0, and so you're just looking at h0 of all those skyscraper sheaves at all those points. Okay, and that means you're just counting the number of points when you check the dimension of that. So that's another way to interpret what's going on. And how's that related to what you have here? Well, it turns out that when you play this sort of game, and it's best to do this actually using a resolution via bicomplex, is that you can resolve this coherent sheaf with firstly O maps to that, because this is the structure sheaf on some sub-scheme. Okay, and then what goes to 0 here? Well, of course, all the things which are 0 on C will go to there, and all the things which are 0 on D will go to the map to the kernel. So the direct sum also maps to there. So you have this direct sum of line bundles here. And it turns out the kernel of this map here is just O minus C minus D. So if you want to work out what is chi of O, C intersect D, okay, you can also use the fact that, well, chi is going to be alternating on this. Okay, so it's just chi of O plus chi of this term here, or minus chi of this term here. So that's minus chi of O minus C minus chi of O minus D. And then you have to add this one, chi of O minus C minus D. And that will also recover this formula. I hope you enjoyed this adventure in pure mathematics.